All right, in section 6.5 here, we're going to learn two new vector field operations, one called the divergence and one called the curl. What we're going to find is that these are operations that generalize from the expressions that we explored in Green's theorem. In particular, in Green's theorem, we had two forms of the theorem, the circulation form and the flux form. Let me find that for you. And in both of those cases, there were these kinds of peculiar combinations of partial derivatives of the components of the vector field. Here in the circulation form, we've got this vector field PQ, and then the integrand in Green's theorem is QX minus PY. And you know, that's just kind of weird, and that's how it falls out from the proof of Green's theorem. And then you go over to the flux form, and again, we have a vector field PQ, and we see that the integrand is this kind of, again, peculiar combination of partial derivatives of the components of f, px plus qy. What we're seeing here is the two-dimensional versions of a pair of general operations called divergence and curl. And what we want to do is learn to compute the divergence and the curl in this section, and then also see how those properties are related to whether or not the vector field is conservative. I think the most important idea in terms of calculating these things is to understand the curl as and the divergence, and indeed the gradient, as all flowing from a single mathematical object that you probably haven't encountered before, and it's this thing right here. This is called, I don't know what it's called, a vector of partial derivatives. It's a really important notion that kind of combines all of the vector operations that we've learned and are learning. What do I mean by this? If we have this symbol, it's called a nabla. Some people also call it del. This is a very peculiar object. It is a vector of first partial derivatives, at least in 3 dimensions. Of course, you can probably imagine how it generalizes to higher dimensions. It's 3 empty partial derivatives. Let's see how this works. We can compute the gradient of a scalar function f by doing scalar multiplication on the right by the scalar function f. That gives me the partial with respect to x, partial with respect to y, partial with respect to z, and then scalar multiplication on the right really just means distribute that scalar in onto each of the components. So we distribute that onto each of these empty partial derivatives. And then we use the notation maybe that we're more familiar with, f sub x, f sub y, f sub z, and we recognize this as the gradient. This is the gradient of f. This is something that you learned a while back in chapter 4, I think. All right, so that's the gradient, and the gradient flows from scalar multiplication of this weird operator against a scalar function. Let's look at divergence. The divergence now acts on a vector field. Let me write the vector field first. So a vector field in 3 dimensions has 3 components, P, Q, and R. And the divergence of this vector field is the dot product of del with the vector field. Let's see what that looks like. Again, I'll write it out longhand. I'm going to shorten these partial derivatives to just look like this, dotted with P, Q, and R. We do that dot product and we get P sub x plus Q sub y plus R sub z. And this is the divergence. And then finally, if we have, again, a vector field PQR and we want to compute the curl of F, it's del cross F. And if we use the mnemonic that we're used to, that's I, J, K, partial with respect to X, partial with respect to Y, partial with respect to Z, and then the components of F, P, Q, and R. And now you start computing. The first component of the curl is the partial of R with respect to Y minus the partial of Q with respect to Z. The second component is minus J, partial of R with respect to X minus partial of P with respect to Z. And then finally, K, partial of Q with respect to X minus partial of P with respect to Y. And you might recognize this one as the circulation form of Green's theorem. That's the Qx minus Py. And remember, Green's theorem applies in 2 dimensions, so when you're doing the curl, you're really just talking about a vector field with no z component. And the only thing that's going to survive that process is this k component. All right. So that's how you compute these. This is how I recommend that you compute these. The book doesn't super emphasize this approach, but I think it's a really useful approach for putting all 3 of these important operations, divergence, gradient, and curl, under one umbrella. And they all flow from this single, what we call differential operator, del. Okay. Let's do a bit of a flyover of the textbook before we get into some of the exercises. So here we get a definition of the divergence. Hopefully you all by now can imagine how this goes into 2 dimensions, how it goes up into 4 dimensions. You just keep adding terms or taking away terms. And here is this operator notation that I just described, and we see the divergence is del dotted with F. Okay, what does this divergence measure? It measures how much a vector field is spreading out. If it's positive, then if it's positive at a particular point, then we can imagine that there's more fluid leaving that point than coming into that point. If it's negative, then we can imagine there's more fluid, or whatever metaphor you want to imagine for a vector field. There's more flowing into the point than out of the point. So divergence is positive when things are diverging, things are spreading out, and negative when things are converging, contracting in. All right, so here we see a vector field, and we can imagine that it's, what's the word? Here it's probably got a negative divergence, but maybe over here it's not quite as obvious what's going on, because we have stuff flowing into this point from, say, the lower right, but stuff flowing out of the point to the upper left. So the divergence is going to kind of measure the net flow in and the net flow out and give you a net value. And if it's positive, then there's a net flow away from the point. If it's negative, there's a net flow in. The only place it's completely obvious where there's a net flow in is right here, when all the arrows are pointing in to that single point. So that's the only place I can definitively say that the divergence is going to be negative there. Everywhere else, it's really just a balancing act and figuring out what the net flow is. Up here, things that tend to circulate like this tend to not have much divergence, but again, you can see these arrows are a little bit bigger out here and a little bit smaller in here, so it's possible that there's some net flow, net divergence either in or out of a particular location. This one, I can pretty reliably say there's no divergence. All these arrows are the same length. They're all pointing in the same direction. At any particular location, there's as much flowing into that point as there is flowing out. The divergence is going to be 0 at that point and really at every point in this field. So calculating the divergence, again, this is a very computational section. I'll leave that to you to explore. Divergence free is when the vector field has, it's 0, the divergence of the vector field is 0 everywhere. This is also called magnetic. I think divergence free or source free is a much more common term. The test for whether a vector field is source free is just take the divergence and see if it's 0 everywhere. Okay, let's keep going. The curl. So what the curl measures is how much at a particular point the field is rotating at a particular location. Another way to think about it is if we go up to this field here and we put our mouse right here and we plant a little ball in the fluid at that point. Is the ball going to want to spin in any particular direction? Is it going to want to rotate? If it wants to rotate here in 2 dimensions, if it wants to rotate at that location counterclockwise, then the curl will be positive. And if it wants to rotate clockwise, the curl will be negative. Here it's not 100% obvious what will happen, but let me give you a little bit of intuition. I can see as I go along this row of arrows that the arrows get longer as I go away from the origin and shorter as I go into the origin. So for example, between these 2 arrows, although they look about the same length, it's reasonable to assume that the arrow on the right is a little bit longer than the arrow on the left. Now, if I imagine that that's fluid flow, and I imagine that there's a little ball sitting between those 2 arrows, the flow on the longer arrow side is going to rub on the ball a little bit more than the flow on the left arrow side. The net effect is going to be a little bit of rotation in the counterclockwise direction. And so I can say pretty definitively that the curl at this point will be positive. Over here, let me see. Over here, these vectors seem to be getting longer as we go away. So let's put the ball here. Now I've got the ball and I've got more rubbing on this side than on this side. And again, I'm going to get a counterclockwise flow. So if I were a betting person and I had access to the full vector field here and took its curl, I'm betting that this vector field is positive everywhere. Alrighty. What about here? You know, at each location radially, it looks like the arrows are the same length. So let me put a ball right here. We can imagine that the arrows that are rubbing along this ball are equal on both sides, and we can expect that there won't be any tendency for the ball to rotate sitting within this flow. So if I were a betting person again, I would say that this field has no curl, 0 curl. And by 0 curl, I mean the 0 vector. Alrighty. Oh, and I misspoke. Curl is a vector valued property. So it's not positive or negative. It's pointing up or pointing down. So let me just recap here. For this guy, if it's rubbing a little bit more on the right, let's put the ball right here, rubbing a little bit more on the right than on the left, it's going to want to rotate counterclockwise. We do the right-hand rule and we get a vector that's pointing up out of the plane, or if it were in the other, rotating in the other direction, a vector pointing down. So I misspoke earlier. Pointing up means rotating counterclockwise, pointing down means rotating clockwise, not positive or negative. Divergence is a scalar quantity. Curl is a vector valued quantity. All right. Once again, computing the curl is a computational exercise, and you can memorize this formula, or you can use this mnemonic. I tend to use this determinant mnemonic to do that sort of stuff. There's a couple of exercises for computing the curl. They can interact with each other. You can take the divergence of a curl and the curl of a divergence. If you take the curl of a vector field and then its divergence, you get 0. What that tells me is that a vector field that's the curl of some other vector field doesn't tend to expand or contract. It is divergence free. The curl of a conservative vector field is 0. For some reason, my web page wanted to just update at that moment. So it's a nice test for conservativeness, and you can kind of see it has the tests for three-dimensional conservativeness built in. So there's this relationship between the curl and conservativeness. Continuing here, we can analyze functions based on, we can sort of test whether they're conservative, etc. Let's just jump into the exercises here and we'll wrap up. Again, this is mostly a computational section. All right, starting with problem 214. The job here is to simply compute the curl. So let's go through that. We identify P, Q, and R. And I'm going to use the mnemonic device. So the curl of F is I, J, K, partial with respect to X, with respect to Y, with respect to Z, and then finally 3xyc squared, Y squared sine Z, and xe to the 2z. All right, and let's work our way through this. We'll do the I component. So that's the partial of this with respect to y. There are no y's here, so we get 0, minus the partial of this with respect to z, y squared cosine z. That's the I component. Minus j, let's do the j component. The partial of this with respect to x is e to the 2z, minus the partial of this with respect to z is 6xyz. And then last component, k, the partial of this with respect to x is 0, and the partial of this with respect to y is 3xz squared. And then we should clean this up before leaving, so let's write it as maybe in component form, minus y squared cosine z, comma, 6xyz minus e to the 2z, that's the middle component, and the final component, negative 3xz squared, and that's how you compute a curl. Okay, let's find a divergence. Remember the mnemonic. The divergence is the dot product of the nabla operator, the del operator, with the vector field. So we're looking at the partial with respect to x, partial with respect to y, partial with respect to z, dotted with p, q, r. This one's easy to memorize, so I tend to just have this memorized. Px plus qy plus rz. And now we'll just we'll go through the components and do the appropriate partial derivative. So the partial of p with respect to x is just yz. The partial of q with respect to y is just 2x squared y z squared. And last, the partial of r with respect to z is 3y squared z squared. And remember, this is a scalar quantity, not a vector quantity. Okay, so this is mixing the gradient and the divergence, and it turns out that there's a very special class of functions, scalar functions, known as harmonic functions, and they are functions that satisfy the following equation. We take the divergence of the gradient of f. Now this is an interesting thing to work out. Remember that the divergence is partials dotted with the gradient, or dotted with the vector field. In this case, the vector field is f sub x, f sub y, f sub z, just the gradient of f. If we do this dot product, we get the partial of f with respect to x twice, plus the partial of f with respect to y twice, plus the partial of f with respect to z twice. So we get these double derivatives, these pure mixed, these pure second partials. And a function f is harmonic if it's 0. All right, this is an important class of functions. For example, if you're studying the wave equation in physics or the Schrodinger operator in quantum mechanics, this operator appears quite often. If you're studying heat flow in engineering math, again, this operator appears quite often. Let's compute let's compute this operation on little f. It's really just the sum of the second partials of f, second pure partials of f. So let's do that. This operator is so important it actually has its own symbol, the Laplacian of f. And whenever you see the Laplace operator, it just means take the sum of this pure second partials. All right, let's do that. The Laplacian of f is take two derivatives in x. Well, we do the first derivative and we get x cubed z squared, so that gives me 0. Let's do two derivatives in y. So we get the first derivative is 3xy squared z squared, and then the second derivative is going to be 6xy z squared. And then finally, two derivatives in z. The first derivative is going to be 2xy cubed z, and the second derivative is going to be 4xy cubed. This is not generally 0, so not harmonic. Now, as I mentioned, computing the divergence is important, but sometimes we want to explore the properties of a vector field at a particular point. Is it diverging? Is it circulating? So here we're going to look at the divergence at a given point. First we have to compute the divergence. So the divergence of f is the partial of the first component with respect to x plus the partial of the second component with respect to y plus the third component with respect to z. That simplifies to 2 plus yz. Now, if we want to evaluate that at the point 1, 2, 1, then we just plug in x equals 1, y equals 2, z equals 1, and that results in 2 plus 2 times 1, which is 4. So if we were to plot this vector field, we would expect to see a net flow away from this point. We can't, it's hard to visualize because this is a three-dimensional vector field, but that's what we would see. We would see a net flow away from the point 1, 2, 1. Similarly, we might want to find the curl at a given point. So this is a three-dimensional vector field, but the k component is 0. Let's compute the curl. That's the del operator crossed with f. We'll set up the whole matrix and the determinant, and we'll plug in e to the x sine y and minus e to the x cosine y. and finally 0. Let's see what this looks like. All right, so we blot out the first component, and we get the partial of 0 with respect to y, which is 0, and the partial of this with respect to z, which is also 0, 0. Minus j, partial of 0 with respect to x, partial of this with respect to z, 0. Plus k, partial of this with respect to x is minus e to the x cosine y, minus e to the x cosine y. That simplifies in component form to 0, 0, and minus 2 e to the x cosine y. Now we want to evaluate this at 0, 0, 3. So that means taking the curl and plugging in 0 for x, 0 for y, 3 for z. Doing so, we get 0, 0. Plugging in 0 for x in e to the x gives me a 1, 0 for y in cosine gives me 1, so that nets out to negative 2. And what we can expect here is that at the point 0, 0, 3, we're going to see clockwise, a net clockwise circulation. And that's because this is pointing into, the curl points into the xy plane. I'm not sure if this will work, but let's try it. Let's plot this in my vector field plotter and see if we can't see that counterclockwise rotation. All right, so let's put in expx, and I've already forgotten what it is, sine y. And then let's do minus expx cosine y. And then click update field. Alrighty, well, there's that. Let's see if we can orient ourselves here. We're interested in the circulation of this field at 0, 0, 3. All right, this field has no z dependence. So this, what it's doing here in the xy plane is basically what it's doing for all z's up and down. Now this is 0, 0. You know, I guess I believe it. Imagine a little float sitting there in the flow. We see by the length of these trails that the vector field flows more quickly over here to the right and more slowly over here to the left. So on sort of a gradient, we get a general decline in the magnitude of these vectors that are flowing down. All right, so let's reposition myself at the origin. We can imagine that vectors just to the right of the mouse are a little bit bigger going down than vectors just to the left of the mouse also going down. So that means that there's a net tendency to want to rotate in the clockwise direction. And by the right-hand rule, clockwise direction, that's going to give me a k vector that points into the plane. And we can see that with the negative 2 here. So that's how one interprets the curl. Okay, finally, find the work done by the force field given by this expression in moving an object from 0, 1 to 2, 0. Is the force field conservative? Okay, had to adjust my notes there for a second. Let's wrap this up and finish this calculation in 258. Look, you're not given a path from 0, 1 to 2, 0, so the only way you're going to be able to do this is if it's conservative. What's the test for conservative that we just learned? We learned that the curl of a gradient vector field is 0. A gradient vector field, of course, is conservative. And so if the curl of this vector field is 0, then this is a conservative vector field, and then we can just use the fundamental theorem of line integrals. Let's compute the curl of this vector field using the usual mnemonic. That's e to the minus y in the first component and minus x e to the minus y in the second component, and then there is no third component. Again, going through the components here, partial of y, partial 0 with respect to y is 0. There's no z, so that's all 0. J, let's look at j here again. Partial x is 0, partial z is 0, so nothing there. Plus finally k. The partial of this with respect to x is minus e to the minus y, minus the partial of this with respect to y is minus e to the minus y. A lot of minus signs flying around here, but there's a cancellation and we get the 0 vector. So conservative. Now we know that the work done as we go between these 2 points, f dot dr, by the fundamental theorem of line integrals is just going to be little f of 2, 0 minus little f of 0, 1. The question now is what's little f, and that's a bit of review of stuff that we did a while ago, finding the potential. So we know that it's conservative. That means that f is secretly f sub x, f sub y. So f sub x is e to the minus y. That means that f must be of the form minus x e to the minus y plus some undetermined constant that might depend on y. Then we take the partial of f with respect to y, and we get x e to the minus y plus c prime of y. Now that has to equal, oh, did I make a sign error here? Hold on for a second. I think I'm okay. I don't know. Okay, yeah, something's not feeling right about this. All right, take the partial with respect to y, and I should get minus x e to the minus y. And there's definitely an issue here, so let's see if I can figure it out. Partial of f with respect to x. If I anti-differentiate, I should get, if I anti-differentiate with respect to x, I should get x e to the minus y. And if I take the partial with respect to y, I should get minus x e to the minus y, and then that has to equal minus x e to the minus y. So those go away. I find that c prime of y is equal to 0. C must be a constant. C of y just is c, and I can now just get rid of the y dependency up here. That's f. Now I compute f of 2 and 0. If I plug in 2 for x and 0 for y, I get 2 plus c minus plugging in 0 for x and 1 for y, I get c and that nets out to 2. So the work done through this field, moving from 0, 1 to 2, 0 is 2. All the suggested exercises are on the table here, and when you've finished those, head on over and try the web work, Chapter 6, Section 5. Thanks.